When we see high voltage lines cutting across the landscape, it's easy to imagine the electricity inside as an instant flood of energy. Flip a switch, and the power is simply there. But inside an alternating current circuit, that instant flow is an illusion. When a surging voltage wave hits a coiled wire, the actual current, the physical stream of particles, hesitates. It drags behind the driving force. This delay is caused by electromagnetic inertia. Just as a heavy physical object resists a sudden change in its velocity, a copper coil resists any sudden change in the flow of electricity. As electrons push forward, their movement generates a magnetic field. Because this is alternating current, that field is constantly swelling and collapsing, and that shifting field physically pushes back against the very current creating it. A standard resistor is a passive component, but an inductor is an active combatant that fights any change in the electrical flow. This behavior follows a principle discovered by Michael Faraday, the law of induction. Faraday realized that a changing magnetic field induces its own voltage. Inside a coil, this creates a self-induced EMF, a force that acts like a physical wall, pushing back against the incoming source voltage. We can map this struggle in a purely inductive circuit. We have our AC source voltage, V, connected to a single inductor defined by its self-inductance, L. This magnetic standoff became the foundation of modern industry. Nikola Tesla harnessed these opposing forces to drive the first rotating induction motors. Because the source voltage and the inductor's self-induced wall are constantly wrestling, the current is forced out of sync. There is a measurable, persistent shift in its timing. To find the exact value of that shift, we apply Kirchhoff's loop rule. In a closed circuit, the source voltage and the inductor's opposing magnetic force must perfectly balance out to zero. Because the source voltage is a sine wave, the math tells us that the rate at which the current changes, expressed as di over dt, is also proportional to that same sine wave. But knowing the rate of change isn't enough. To find the actual instantaneous current flowing through the wire at any given moment, we have to integrate the voltage wave over time. The rules of calculus dictate that when you integrate a sine wave, it physically transforms into a negative cosine wave. This resulting equation for current reveals a specific phase constant, a mathematical signature of a 90-degree delay. Look at the peaks. When the voltage hits its peak, the current is just crossing the zero line. It hasn't even begun to climb. The calculus provides the proof. The current is forced to lag the voltage by exactly pi over 2, or 1/4 of a full cycle. To make this delay easier to track, engineers use phasors. A phasor is a rotating vector, an arrow used to represent out-of-sync alternating quantities as simple geometry. If we freeze the circuit at a single instant, we can draw the voltage phasor as an arrow pointing straight up the vertical axis. This diagram shows the permanent relationship. The current vector, I, sits on the horizontal axis, locked 90 degrees behind the voltage. Now, let them rotate. Both vectors spin counterclockwise, but the current can never catch up. It is forever trailing a quarter turn behind the voltage. This model locks the abstract calculus into a tangible shape. The 90-degree lag is a geometric certainty. When Tesla and his contemporaries scaled this up to industrial powerhouses, they had to account for how these magnetic interactions restricted the flow of power across the grid. This restriction is called inductive reactance. It is the dynamic equivalent of resistance, and it is calculated by multiplying the source frequency by the inductance of the coil. Because frequency is part of the equation, the inductor's behavior changes depending on the speed of the source. As the frequency of the AC voltage increases, the inductor's barrier to the current grows stronger. If you turn the frequency dial higher, the magnetic field barrier intensifies, choking the current flow down to a trickle. At low frequencies, the current passes through with ease. This makes the inductor a perfect filter, capable of selectively governing a circuit based on nothing but the speed of the signal. This leads to a final paradox. Despite creating a massive barrier to the flow, a pure inductor consumes zero net power. It operates in a breathing cycle. For 1/4 of a cycle, the inductor draws energy from the source to build its magnetic field. But in the next quarter, that field collapses, returning every watt back to the source. Because the waves are out of sync, the power wave swings equally above and below the zero line. The positive and negative cycles perfectly cancel. We exploit these lossless properties every time we turn a radio dial. We use inductors to block thousands of unwanted frequencies and select a single station, all without wasting the energy we need to hear it.